All right, so we are looking at uniform or constant acceleration, which is way different than uniform or constant speed slash velocity. So remember that when something is accelerating, okay, the object is either speeding up, slowing down, I'm just going to push slowing, or changing directions. And acceleration is the rate at which that velocity changes. Okay, now we're looking at uniform acceleration, when something speeds up or slows down by the same amount every second. Okay, uniform acceleration. So what does this type of motion look like? So first of all, the velocity is going to either increase or decrease by the same amount every, we're going to say 1 second. Okay, you could say every 0.1 second, or every 0.5 seconds, or every 2 seconds. Okay, but the velocity is going to either increase or decrease by the same amount every 1 second. So what does that look like? So let's say our acceleration is 1 meters per second squared, or 1 meter per second per second. And our initial velocity is 0, okay? What that means is that after 1 second, the instantaneous velocity is 1 meter per second. After 2 seconds, the instantaneous velocity is 2 meters per second. And after 3 seconds, the instantaneous velocity is 3 meters per second. So the velocity, or the magnitude of the velocity, is increasing by the same amount every, in this case, 1 second. Okay, that acceleration is uniform. Another characteristic of uniform acceleration is that the interval distance either is going to increase or decrease by the same amount every, we'll say, 1 second. Okay, again, but that could be 0.1 second, 0.2 seconds. So what does that mean? I have a picture down here to help us. So this car is accelerating at a uniform rate to the right. So it's speeding up, moving to the right. Okay, this is the interval distance, this distance right here. It's the distance between two positions, successive positions, okay? So let's say this is how far the car travels in the first second. This is how far the car travels in the second second. This is how far it travels in the third second, and so forth, okay? So I said up here, the interval distance in this case is going to increase because the car is speeding up, but it's going to increase by the same amount. So I'm just going to put numbers with this to help me out. Let's say that the interval distance here is 1 centimeter. That means in the second second, we're going to increase the interval distance by 1 centimeter. And so that would be 2 centimeters, which is 1 centimeter greater than the previous one. The interval distance here would be 3 centimeters, which is 1 centimeter more than the 2 centimeter previous interval distance, okay? The next one would be 4 centimeters, okay? So the interval distance is increasing by 1 centimeter every, in this case, 1 second, okay? And again, that could be increase if it's speeding up, or that could be decrease if it's slowing down. So another characteristic of uniform motion or uniform acceleration is the slope of the velocity versus time graph is constant. So we have a velocity versus time graph, and we know that the slope represents the acceleration. So if this slope is constant, meaning we have a straight line, then we have a constant or uniform acceleration, which means the acceleration stays the same. It is not changing. Okay, next we're going to look at the 4 equations, 4 kinematic equations that we use when something is accelerating at a uniform rate. And I'm going to show you how we derive those equations and where they come from. So our first kinematic equation that we're going to look at, and this is on a formula chart that you'll all get on equation sheet, is Vx equals Vx naught plus Ax times t, okay? Now let me explain what this is. The x here represents that we're in the horizontal dimension, okay? So this and these equations only work for like single one-dimensional motion, okay? The x naught, the Vx naught, that's the initial horizontal velocity. And then sometimes I will write an F here, that just stands for final velocity, okay? So we're talking about uniform acceleration, and this is our first kinematic equation. And where does it come from? Okay, so here's the thing. It actually comes from our average acceleration equation, which is the change in velocity divided by the change in time, which we can break down into final velocity minus initial velocity divided by the change in time, or just t, okay? Here's the thing. If we have a uniform acceleration, that is also our average acceleration. So if our uniform acceleration is 1 meter per second squared, well, that's our average, because if we're going 1 meter per second squared, 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 that's uniform acceleration. That is also our average acceleration. So these two equations are actually the same thing, okay? It's just this one is solved for acceleration, whereas this is solved for the final instantaneous velocity, okay? So what we're going to do is we're going to rearrange this equation to solve for the final velocity. So we're going to multiply both sides by t here, and that is a times t equals Vf minus V naught. And then we're just going to add the V naught over. So our equation is Vf equals V naught plus A times T. And the only difference here is they write a little x here to represent that horizontal dimension. Okay, our second kinematic equation is not on the yellow sheet or on your equation sheet that you'll get. So looks like this. It's delta x, which is the displacement, is equal to 1/2 times Vx initial plus Vx final times delta t, or we can just say there just t. Okay, so that's the second kinematic equation that we can use when the object is accelerating at a uniform rate. Okay, notice here that we're solving for delta x. So now where does this equation come from? How do we derive this equation? Well, it all comes from a velocity versus time graph. So if we have a velocity versus time graph that looks, let's say, like this, this would be uniform acceleration, okay? Notice our initial velocity here is 0. Remember that the area here under this line, the area represents the displacement, okay? And so if I were to find the area of a triangle here, that would be 1/2 base times height, okay? In this case, our base would be delta t. So let's go ahead and just substitute here delta t in for our base. And because our initial velocity is 0, our height here is just the final velocity. So let's go ahead and substitute their final velocity. So you can see where that equation comes from. It comes from the fact that the displacement is the area under that line, okay? And we have a constant or uniform acceleration. Now, what if though, what if the initial velocity is not zero? Okay, so velocity versus time graph, but let's say, okay, so this is zero velocity. Let's say it looks something like this. Again, it still has to be a straight or constant slope because we have uniform acceleration. But let's say the initial velocity is not zero, okay? So here, the area here represents the displacement. The area represents the displacement, but we don't have a triangle here. Now we have a trapezoid, okay, a trapezoid. And so with a trapezoid, this would be the A length, okay, that's our shorter length. This would be the B length, and this would be our height. And for a trapezoid, the area is 1/2 times A plus B times H, the height, okay? So in this case, our A right here, our A would be the initial velocity. So let's substitute here. A would be the initial velocity. B here would be the final velocity. So we're going to substitute the final velocity here in for B. And then the H here would be our change in time. So we're going to substitute our change in time here. So you can see where that equation comes from, how it's derived, okay? And so again, this is our second kinematic equation. And notice that in that equation, acceleration is not expressed. So we're using this equation when we know we have uniform acceleration, but we don't know the value for that acceleration. Okay, for our third kinematic equation, and this one is on the sheet, it looks like this. It's x, and you can think of that as the final position, equals x naught plus vx naught times t plus 1/2 ax times t squared. I'm going to scroll that down so you can see that. Okay, so sometimes I will write this one a little different, okay? I will subtract x naught over, and that gives us delta x, which is the displacement or change in position, equals vx naught times t plus 1/2 ax times t squared. So sometimes I write that a little different. Just know it's the same thing. It's just this one is solving for the final position after so many seconds, and this one is solving for the change in position or the displacement. So where does this equation come from? It's kind of along the same lines. If we, as the last one, if we have a velocity versus time graph, that looks like this, velocity versus time, and again, we have to have that uniform slope or that constant slope. Now let's say that the initial velocity is not zero, okay? We know that the area under that, the area under here, represents the displacement. The area represents the displacement, okay? Now, we could use the trapezoid formula, or we could do it this way. We could break this down into the rectangle part, so this would be the rectangle part, and the triangle part. And we know that the area of the rectangle part plus the area of the triangle part equals the total area, which is the displacement, the change in position, okay? Now, for the rectangle part here, it's base times height, okay? In this case, the height is the initial velocity, okay? And the base here is the time. So this is the base is the time, and the height is the initial velocity. So you can see that and that look very similar. Okay, so the area of the rectangle is going to be the initial velocity times the time. Okay, then we also have the area here of the triangle, which is 1/2 base times height. Now here again, the base is the time, and the height is going to be this, this height right here, which is the final, or the velocity, okay, the change in velocity, the change in velocity. So how do I get from this to this? Okay, how do I do that? So it's a little different. So remember, the change in velocity is the acceleration times the time. Think like acceleration is the change in velocity divided by the time, okay? The change in velocity is the acceleration times the time. So if I substitute that in for the change in velocity, that's 1/2 t times a times t, okay? Notice we have two t's, so that would be 1/2 a t squared. So that's how we go from here to here. So the area of the triangle is 1/2 a t squared, and that, the area of the rectangle plus the area of the triangle, equals the total displacement. Okay, so that's where that equation comes from. This is the fourth kinematic equation. I'm not going to show you how to derive this one just yet because it requires some knowledge of energy and kinetic energy and gravitational potential energy. So yes, those are our 4 kinematic equations that we use when an object is accelerating at a constant rate.